In the last video, we looked at how atmospheric pressure could be measured experimentally using a barometer, which is an apparatus in its simplest form. Looks like this. It's an inverted glass tube that's closed on the end, filled with mercury. You turn it upside down in a dish of mercury, and you'll see the fluid pull away from the end, and there'll be a vacuum up here. The height of the fluid column that's left is a measure of atmospheric pressure. How does that work? Atmospheric pressure presses down on the mercury in the dish. So atmospheric pressure is pressing down here and here, and it drives the fluid up in the column until the weight of the fluid column balances the atmospheric pressure out here. So the pressure exerted by the fluid column has to balance the atmospheric pressure. And that's going to allow us to calculate the pressure of the atmosphere from the density of the liquid that we put in there, times the acceleration due to gravity, times the height of the fluid column. The density of mercury is something like 13.55 grams per cubic centimeter. Now I would have to turn that into kilograms per cubic meter before I could get the pressure out in SI units. The acceleration due to gravity we saw was 9.8 meters per second. And this height, typically at sea level, is about 760 millimeters. So you can do this calculation every time. You'll have to do a unit conversion here to get this in SI base units, kilograms per cubic meter. Then you'll have to turn your millimeters into meters, and then you'll have to multiply those three things together, and that will give you your atmospheric pressure in pascals. But we can simplify things a little bit by defining a new unit. One unit that we can define is just to use the millimeters of mercury in the barometer directly as a unit. If we use millimeters of mercury, (760 millimeters of mercury is usually what we see. So we can use millimeters of mercury directly as a pressure unit. In Frostburg, if you've got 713 millimeters of mercury, that's normal atmospheric pressure in Frostburg. Down at sea level, it's 760 millimeters of mercury. Now, you can call millimeters of mercury Torr as well. It's named after an Italian lawyer, Torricelli, who invented this setup. A torr is the same thing as a millimeter of mercury. So both of these are pressure units. Now, how do they relate to pascals? Well, you can see how they relate to pascals through this equation, but there is an easier way to relate them. 760 torr, or 760 millimeters of mercury, those are interchangeable, I'm going to define as normal atmospheric pressure, or standard atmospheric pressure. The atmospheric pressure down in Baltimore, down at sea level, averages out to be about 1 atmosphere. Their barometers will read about 760 torr. So the standard atmospheric pressure, or just atmosphere for short, has an abbreviation ATM. I'm going to say 1 ATM, 1 normal atmospheric pressure, is 760 torr. And how does that relate to pascals? 101.325 pascals is an atmosphere. So I can do some unit conversions here depending on how I want to express my pressure. The worksheet has you doing this. For example, if I have, I don't know, 725 torr, and I want to write that in atmospheres, I will have to know that 760 torr is 1 atmosphere. That would give me the pressure not in torr, not in millimeters of mercury, but in atmosphere. It's just a unit conversion, and I'm using this as a conversion factor. And you've got to do that with one of the problems on the worksheet. That will get it to atmospheres. If I wanted to convert atmospheres into torr, say I had 1.013 atmospheres, so a little higher than normal atmospheric pressure, and I wanted to write that in pascals, I could use this as a conversion factor. Atmospheres would cancel out, and that would convert it into torr. Now this is kind of a funny number. It's not a nice round number. So people have defined something else that they use when they're talking about weather reports. If you were going to do weather reports, you would always be having these huge numbers if you were doing them in pascals. They define a unit called a bar, which is very close to being a 1 atmosphere. It's 100,000 pascals even. Let's know this one. Now this one, since it's not a nice round number, I would always supply to you on tests, so you wouldn't have to know that 1 atmosphere is 101,325 pascal, because I'll give you that number, and you can always look it up if you need it. But you've got a problem that asks you to convert between bars and atmospheres. Like suppose I had 0.931 atmospheres, which is close to atmospheric pressure in pascal, and I wanted to turn it into bars. Well, I could convert atmospheres into pascals. 1 atmosphere is 101,325 pascals, and then I can convert pascals into bar. 100,000 pascals is 1 bar. So that would give it to me. Atmospheres cancels, pascals cancel, and that gives me bar. So these are just some unit conversions that involve these 2 unit conversions that I'd like you to know. And there's another one. Now when you're filling up your tires at sheets or whatever, and you go to the pump, they read off in English units, which are pounds per square inch. That's a force over an area, and sometimes people call that PSI. And atmospheric pressure is about 14.7 PSI. Is 1 atmosphere. You may see that in some of the problems on the homework. They wouldn't expect you to know this. You could go look it up. Also, when you're filling up your tires, for example, my tires on my car, they want to be full to 34 psi. So I set the gauge to 34 psi, and then I fill it up. And when you're reading a tire gauge, it's telling you what the pressure is in excess of atmospheric pressure. Tire pressures are called gauge pressures. And whenever you have a gauge pressure, that's pressure in excess of atmospheric pressure. So when I fill in my tires to, say, 34 psi, actually I'm filling them up to 34 psi plus normal atmospheric pressure. Might be something like 15. So I would have to add normal atmospheric pressure to the gauge pressure in order to figure out what the true pressure in the tires was. So the tire gauge, only reads the pressure in excess of atmospheric pressure. Now, when I'm reading gas pressures, I use a device called a manometer very often. A manometer is for reading gas pressure. Gas in a tank, gas in a tire. A barometer is for reading atmospheric pressure. What does a manometer look like? Suppose I've got some gas trapped in a little bulb here. I hook it to a little U-tube. And I mean U-tube. And the end of that U-tube, if it's closed, I call this a closed manometer. Now to get it to work, to get it to actually measure pressure, I've got to have some kind of fluid trapped in the U-tube here. Usually it's mercury, but sometimes it can be oil or something else. Let's, for simplicity, assume that it's mercury, because that's often what it is. How would I read off the pressure of the gas from this U-tube? Well, I'd have a ruler or something next to it where I could read the difference in heights here. And I'll call this H. And then I can simply use my equation that we derived a couple of videos back for fluid height to calculate what the pressure of the gas was. The D is the density of the fluid, remember? The G is the acceleration due to gravity. It's a constant. And the height is the height that I read off the closed manometer. It's the difference in heights between the two arms. Now, what happens if your gas pressure increases? What's it going to do to that height? If you have more pressure, more gas pressing down on this end, it's going to make this end go down and this end goes up. So you're going to get a bigger height. The bigger this height is, the bigger the pressure of the gas is. So this is the pressure of the gas in this case. Now if it's mercury, you can do away with this equation and just read it off in Torr. For example, if I see that the height is 25.0 millimeters, the H, I can just report the pressure as the pressure of the gas is 25.0 torr, or 25.0 millimeters of mercury, I can say. As long as this is mercury in here, this is going to work. If I have oil or something in there, I'm going to have to put the density of the oil in here. So this is only going to work if I have mercury in my closed manometer. And if I wanted in pascals then, I could convert Torr into pascals like this. I know that there's 760 Torr in 1 atmosphere. And I also know that 1 atmosphere is 101,325 pascals. So I would have to do a unit conversion using the unit conversion factors that we were talking about on the previous page if I wanted it in pascals. But I could read it right off in Torr, and that would keep things simple. Now, you can also have an open manometer, which reads the gauge pressure. So here's the gas. This is open right here. And here's the U-tube again. But this time it's open on the top. And I'll call this an open manometer. And suppose this is filled with mercury again. I would again look at the height difference between the two arms. Call it H. The pressure of the gas in this case is the pressure of the fluid column, which I could read off in Torr if that was mercury. Plus, now what else do I have here? If it's open on the top, the atmosphere can get in, so it'll add the atmosphere in here. So just the mercury column would give you the gauge pressure. This would, you'd have to add that to atmospheric pressure to get the actual pressure of the gas. So suppose this was 25.0 millimeters and we had mercury in there. Then I could write this as 25.0 torr. And if I knew my atmospheric pressure, take the typical Frostberg atmospheric pressure in torr, I could add 25 to 713 to get the pressure of the gas in there. In other words, the gauge pressure, the pressure in excess of atmospheric pressure is 25 torr. I would add that to atmospheric pressure to get the pressure of the gas. Now, if I had something like this with an open manometer, what would you say about the pressure? Let's suppose that the difference in the heights here was 10 millimeters and we had mercury in here. Now take a look. The height here is really down on this side. It's kind of a negative height. So what's happening here is that the pressure of the gas is less than the pressure of the atmosphere. So this is actually a negative height. It's lower on this end than it is on this end. And that means if I use my equation for the open manometer here, the pressure of the gas is still going to be the pressure of the fluid column. On this side, the fluid column is missing, so it's negative. Say this was 713, and this was down 10. If that's millimeters of mercury, that's the same thing as torr. So I'd take 713 minus 10 in this case. So my gas pressure would be 703 torr. So that's something a little bit tricky about reading an open manometer. It's reading the pressure relative to atmospheric pressure.